You've probably heard of ray tracing because it's a big thing at the moment, but you've definitely seen it at some point in your life because it's heavily used in games, rendered art, and films and visual effects. It's massive over there, and it can render things in very, very high quality detail. And I want to go over how it works and also why we eventually went from rasterization to ray tracing. I mean, rasterization is still used, but why I eventually said we need something that can do a little bit more detail. To start off with, I want to show you how good ray tracing can look. So here's a video of someone playing Cyberpunk with the highest ray tracing mods. Now, this is absolutely insane. To me, this is photorealistic. Why does this look so good? And that is because of things like the shadows down here, the reflections in the car. That is all done thanks to ray tracing. So traditionally, we would use something called rasterization. Now, to give an overview of 3D graphics, what we have is we have a series of polygons in 3D space. And what we're trying to do is generate an image of these polygons, right? And what we would use is something called rasterization, which is a way of almost painting pixels onto your screen. Now, rasterization is very, very, very optimized and very quick, but it struggles with handling things, more complex light interactions like you saw on there, like the reflections and the shadows and stuff like that. So I want to go over quickly how that works so that we can then show you why we eventually started using ray tracing and things like that. So let's create a very simple scene, right? So let's say we have a floor here. Oh God, I'm really not very good at drawing. And let's just have very basic triangle here. And just so I can really show off how this works, we'll have a red square behind it. Right, what do we do now, right? We have this scene. So we need to have a camera in this scene. So we'll have a camera up here. And now you're probably going, how do we get the camera here? I'm not going to go into that right now, but you basically have a series of matrices that you multiply each of these points by, and you'll get that camera. I believe there's a video on that on this channel already. What you'll then get is you'll get an image up here like this, and you'll have these vertices for these shapes in 2D, basically. They'll look something like this. One here, and say you have your triangle here. So you have your vertices on your image plane. How do we actually generate the pixels for these shapes, right? That is when you rasterize it. So it would look something like this. You'd have your vertices here for this triangle, and you want to basically color in the pixels that are inside this triangle. So let's just draw the outline here. Essentially go, okay, this pixel looks good, this pixel, this pixel, this pixel, and yeah, that pixel's in enough, that one's not in enough. And basically what you do is you'll color that all in and you'll get a triangle there. And that is what you will do for each of these. Now, you're not generating a pixel per se, you're generating something called a fragment at the moment, because what you do is you do it for every single shape in your scene. So you'll do that for the triangle, and you'll also do that for the square.
Well, even if they both in the same pixel?
Yeah, because you're not generating a pixel quite yet, it's a fragment. And what you will then do, you have all your fragments, go, okay, which one's close to the camera? You reference your Z buffer, it's called, and you'll go, okay, green triangles first, let's just render that fragment as your pixel. So then what you get is eventually you get, I'm trying to represent these as pixels, I'm just going to shade it in.
Life's too short then.
Life's too short, yeah. So you then get something like that. What I'm trying to show, green triangle in front of the red triangle. Okay, so what you can do better than that. We can do better than that. So another thing you'll do is you'll use textures. So you'd rather than interpolating between colors on your shapes, you would use a texture map, and then you basically just plonk your texture on top. It's dead easy, right? But let's do some more complex things. Let's do lighting, right? And I'll show you how that works. So let's just say we have a light source here, for example. We have a little sun there. Typically for lighting, you'd have, let's say, some ambient values, some diffuse values, and specular values. And what happens is that if your camera is, let's say, here, and the light rays are bouncing off this object And essentially you use some calculations to figure out what that lighting should be at each fragment. So you go, okay, light source is here, our normal vector is here, our camera is here, therefore these are what the diffusion spectral stuff looks like. And you get a nice little thing like that, and it looks pretty good. But the issue is that all you're doing is saying, our light source is here, let's just guess sort of what the lighting effects are. And the issue is that, let's say there is another, let's say, little like flying saucer here, okay? When you calculate your lighting values, you're not accounting for objects in the way. Essentially, you would still render these lighting effects on your shapes. And that's not right. It doesn't look correct. And you can do things like shadows. You could generate these things called shadow maps that do that, but they're an extra step that you have to do. And then what happens if you do, let's say, shadows, or reflections or refractions, is that they're so incredibly hard to calculate with rasterization that you get these shader functions which are millions and millions of lines long. Okay, maybe not that much, but you get these massive bloated shader functions just trying to figure out what these should be. And then what happens is that your quality just isn't lifelike. It's good, but it's not as good as it can be. It doesn't have that special source to it. Now, maybe what we should do is we should maybe go outside and I can show you how light works in real life and show you how we can implement that in modern graphics. It's lunchtime. Thankfully, the weather's actually been very kind to us here in Britain. So how are we seeing this right now? What is happening is that the light is coming down from the sun or wherever other light source is here, and it's bouncing off the ground, the lake, it's bouncing around all that, and then it's hitting the back of our eye, and then we are technically rendering an image in our brains. Now, if you go back to how what I was talking about with rasterization, that did not do any of that. It's not like it is in real life. While ray tracing is almost a little bit like the opposite of how light works in real life. So as I say, light comes from your light source, it's bouncing around and hitting your eye. What we do in ray tracing is that you have your camera, you then shoot rays out through your camera and track where those rays go. For example, if I wanted to render the ground here, what we would do is we'd shoot a ray out, it would hit the ground and we'd go, okay, that's where our surface is. And we'll go, okay, that's where our light is. Therefore, we can calculate the lighting effects. And it's why I'm able to have a shadow here, because what we would do if we're going to render this shadow is we'd shoot a ray out in our camera, it would hit the ground, and then we go, hang on, our sun is up here. And when we shoot a ray from the ground to the sun, there's an object in the way. I am in the way. So therefore, we know that that light cannot hit that surface. Therefore, we don't render anything. And you see how that's much more intuitive than generating these crazy shadow maps and having these large, crazy rasterization shaders. You see how interesting the light, how that's bouncing off that water over there. And sometimes with stuff like that, you can see a rainbow. And that is because the light is interacting with those water particles in a very interesting way. So trying to model all this in rasterization is difficult, to say the least. But what we can do is use ray tracing to follow the light and get a much better rendered image because of it. So now I've gone on about how ray tracing works, so maybe let's go inside and I can show you, draw some diagrams and show you how that works on the computer. I've redrawn this scene again, start from scratch, and I'll show you how you can render this with ray tracing. So I mentioned outside that you shoot rays out into your scene. There are different ways you can shoot your rays out, the angles you can shoot your rays out. So there's like orthogonally, which is they're all straight, or from a perspective where they're like that, like how the human eye renders an image basically. So let's shoot 3 rays out here. So let's do one like that. Let's do one like that, for example, and then let's just do one like that. Now, the first thing you've got to figure out if you're doing some sort of ray tracing is what objects have we hit once we've shot the ray out. So here we've hit this object, we've hit that object on this ray, we've hit that object here, we've hit that object here, and we've hit that object here. The main thing that slows ray tracing down is figuring out what objects we have hit in this scene. So as you can see on here, we've hit various objects, and how do we figure out what, oh, there's one, should be one here. How do we figure out what objects we've hit? Now there's many different ways of doing that, and that's a whole separate video in itself potentially, because that is how we optimize this process. But let's just say we can figure it out for now, okay? So we figured out that we've hit these objects here. So what we do is go, okay, which was the first object that we hit? Okay, we hit that object, we hit that object, we hit that object. Okay, cool. So we now know the colors because we've hit these objects. So that one would be black, let's say it's a black surface, hit black, green, green. Okay, when we did rasterization, that was the first thing that we did here, was figuring out these colors. We've just done that by shooting rays out and seeing what it's hit. So how do we calculate lighting? Okay, we have our light source up here. What we then do, typically, is we'll shoot out another ray up here towards our light source and go, okay, firstly, can it reach the light? Okay, these two can, this one can't, because it's hit the triangle. Therefore, that is a shadow, okay? See how much easier that is than having to render a separate shadow map and incorporate all that into your shader functions. You just go, I'm going to shoot out another ray, didn't hit it. Okay, there's something in the way. That's it, right? That is all you need to do. And to calculate the lighting is actually quite similar to how the equations we use for rasterization. It's just you calculate your diffuse and your specular values, and then you just go, okay, that's the final color. And that's the color of your pixel, basically. You figure out the color of your pixel by following that ray through your scene, calculating the lighting, calculating if there's shadows, and then basically backtracking and go, that's our pixel color. Now, hopefully I've explained that reasonably well. Let's do something slightly more complex here. Let's imagine that down here, let's say that this is no longer a floor and that we have a mirror here, okay? This is what I was going on about outside that ray tracing can do very well. How do we handle something like a reflection? So what you do, you shoot your ray off down here, it hits that surface, and then you go, okay, it's a mirror. Let's bounce this ray off. Boom. Now that ray has gone up here, and it's hit that triangle here. And you go, okay, now I've hit the triangle, you calculate your lighting. It's occluded by that, therefore you don't render any light from that light source, and you backtrack there, and you basically, what you'll see when you render the image is you'll see the underside of this triangle, because that is how it would be. You have a mirror, you have a triangle, you hit that triangle, you render that image. You see how much easier that is than having to faff around with these shader functions and create something crazy in rasterization. It's built, ray tracing is so good because it mimics how real life works. So things like reflections and refractions, subsurface scattering suddenly become a lot more easy.
Can I ask a question?
Yeah.
Obviously in the light source scene where we were outside, the sun is so bright, things are bouncing off all sorts of things. In graphics, they often have more than one light source, don't they?
Yeah.
How do you deal with that?
So if you have more than one light source, what you, let's say is the one here, what you do when you check and you go, okay, what's our lighting? If we're let's say a shadow, you shoot off a ray there and you shoot off a ray there, and you go, okay, let's say you're this one, and this isn't a mirror anymore, we're back to flat object. You go, okay, that is in occluded, so you don't render any light from there, but that one isn't. Therefore, what you get is you get like a shadow going like that.
So it's just basically some kind of summation of what different things are at that point.
Exactly, yeah. So that's how you can render really cool multiple light scenes, because it can do that, right? But with every light source, you've then got to figure out an extra calculation of shooting another ray out, and you see how that can get very, very complicated. But it's a lot easier than rasterization for calculating light.
And just one other question before we go to whatever's next.
Yeah.
Each ray is one pixel, so a pixel is a ray and a ray is a pixel.
Typically, yeah. Normally, there are other more complicated things you can do, but whole different subject entirely. We won't go into that, otherwise it'll be an hour-long video. What I want to show you is a comparison between a ray tracer and a rasterizer. Now, we have our rasterizer here, which is OpenGL, and on the right we have a ray tracer. Now, this is a ray tracer that I built while I was at the University of Leeds. Just to make sure everyone is aware, my ray tracer is not very good. It's very unoptimized. It's not nowhere near as good as it can be. However, it is a good comparison, and it's good, and I can show you the benefits of using a ray tracer and the drawbacks. Add our lighting here. Firstly, I want to just talk about while I'm setting this scene up. Look how slow it is to do anything here. The reason why this is so slow is that for every single ray that you shoot off, it checks every single triangle in the scene to see if it's hit it. Now, let's say you've got a 600 by 600 pixel image here. That is 600 by 600 rays checking every single triangle in this scene. Let's say it's 10 triangles. So 600 times 600 times 10 calculations every time, which is just why it just is why it's slow. And that's not including the lighting calculations and checking shadows and stuff like that. My point being with that is that while ray tracing can render very nice images, it's a lot slower than rasterization, which is why for a game like Minecraft now uses ray tracing, I've heard, but the very early versions of Minecraft only use rasterization because why not? You're just rendering blocks. There is no crazy reflections, refractions, crazy lighting effects, and you wouldn't need to because it's just a nice game with some blocks. So I've finally set up this scene here, and what I'm trying to do is make it like what we were doing down here. So we have a triangle over a ground plane here. Now on the left you have your OpenGL, on the right you have my ray tracer. They look about the same, and they should, because we're not doing anything crazy here. The light is pretty much the same in both scenes. We're not doing any reflections, refractions, or anything crazy like that. But what I can do on the ray tracer is do shadows. Our light source is up here. How this works is the camera would shoot a ray out here. It hits this ground plane here, and we go, okay, let's shoot another ray up to your light source. Oh wait, there's a triangle in the way. Don't render any light there. That's how you do a shadow. And that is how the whole scene is rendered, by shooting rays out. Let's say you do put a point here, shoot a ray out, it's hit our ground plane, shoot another ray out to the light, nothing in the way, therefore we can just calculate the lighting effects there. Obviously I've gone on and spoken about, this is how ray tracing works, but ray tracing is a big subject, heavily researched. There are many, many ways of calculating your light, calculating different effects like this, but essentially the underlying thing is you are handling rays, shooting rays out and tracking them. That is what ray tracing is, okay? This is just one way of doing it. We've booted up a more complex scene here. Now this is called the Cornell box, which is basically, if you want to compare how good a graphics engine is to other scenes, other ray tracers and rasterizers, what you do is you set up the scene of the Cornell box here, and then you can get a direct comparison, which is what we're doing here between OpenGL and my ray tracer. Now, this framework is built by the University of Leeds. I'm just using it to show a comparison. So on the right is my ray tracer that I built, and on the left is just OpenGL. One thing I want to mention here is that I am using probably the worst way of using OpenGL. The lighting is directional light, so it looks pretty muggy. You can use positional lights to make this a little bit better, and it will look similar to the ray tracer here, but what it can't do, unless you go into your shader functions and change stuff, is this shadow down here. So what is happening is we have a light source here, a shadow here, and it's rendered like that, and I think it looks pretty decent, right? But what's something cool we can do now? What would happen if we set the walls either side to be a mirror? Well, I'll show you how that works. It takes a while to calculate, which I think proves my point of, while ray tracing can render stuff like this, it is a little slower than OpenGL, which can render like that. So here we go. We've set both of these walls to be mirrors, and as you can see here, it's rendering the side of the box here. Now let me show you how it can render that shadow there. What is happening is we are shooting a ray through your camera into your scene. It is hitting that mirror and going, okay, it's a mirror, let's reflect off it. It is reflecting off that mirror and hitting the floor, let's say here. Now, we have our light source up there, we are shooting another ray towards our light source, and it's going, we've hit the side of this box here. Therefore, there is no light hitting here, so don't render any diffuse or specular lighting, and then that's how we get that final pixel color, you see? So it's all about following those rays and figuring out where they are in the scene, what the color should be on the surface, and then what the lighting should be, if it's in a shadow, if it's refracted through an object, if it's done anything like that. Ray tracing is very good for rendering very high quality scenes, but it is much slower than traditional rasterization. So if you're a games developer or an artist, you've got to decide if you want speed, but maybe a little less quality, or you want it to be maybe a bit slower, but you can render stuff like this seamlessly.
The further away you get from where your images were actually captured, the more noisy your Gaussians are going to get.
Exactly. So if you look over here, can you see?
And so if we just sort of feel our way towards it by taking off little bits of noise at a time, we can actually produce an image. Right? So you start off with a noisy image,